This lecture is about cross-validation. This is a way that you can estimate the out-of-sample error rate for predictive functions that you're building. So the key ideas here are that we're going to be taking the training data. Remember that we broke our data set up into a training data set, a test data set, and maybe a validation data set. And here we're just going to be focusing on the training data. We're going to subsample that in specific ways in order to build estimates of the error rate that we would get if we applied our prediction function to the test or validation data sets. The goal here is again to avoid overfitting. This is one of the key issues in predictive functions. You don't want to tune your predictive function too closely to the data set that you have in hand. The other goal is to make your predictions generalizable or to compare different potential models and pick the one that you think will work the best on a new data set. So this is going to be focusing on these three components of the building a prediction function process. So first, we're going to be talking about picking features, picking prediction functions, and using cross-validation to be able to determine which of those features and predictive functions are going to work best. So remember that the study design is, in general, you might have a training data set, and then you might have what's called a test data set and a validation data set. You're going to build models on the training data set, then you might test them only a few times on the test data set to do fine-tuning, and then apply it exactly one time and no more to the validation data set, and you'll never use any of the validation data set to build your predictive function. But one goal you might have is while building a predictive function on the training data, you might want to know how well is that predictive function going to work when you apply it to the test data set. And so the goal of cross-validation is to be able to estimate that error rate, to estimate how well your predictive function will work on that data set. I'm going to use a really simple model to explain how overfitting can be a problem. So in this example, there are two variables, x and y, that are going to be the variables that you're going to be using to predict. And then there's z, which is the outcome, which is either equal to 0 or 1. So first thing that I do is I plot the x and y values and I color them by the z values. In this case, z is actually unrelated to x or y, so there's no predictor for z that is in principle good on the basis of x and y. But you can see that in this particular example, it looks like the z values that correspond to the color blue kind of cluster here in the middle. So one thing that we could do is we could actually build a classifier that says, okay, if your y value is less than 0.6, so less than about here, and greater than minus 0.2, so about right here, we're going to call you a blue point. So basically we're just going to sort of section off this part of the data set, and we're going to classify you as blue if you're in that part of the data set. So on the right here, this is just our predictions based on the training set. And it turns out, look, we get perfect prediction. We get exactly the same points that are colored blue and the exact same points that are colored green because we've designed it to be a very good classifier on our training set. But suppose that we generate a new data set. So now we've generated a new data set, again, using just normal data for x and y, and then unrelated set of binomial data for z. And if we plot on the left the x and y values and the corresponding z values in color, we can see that now the blue dots are a little bit more scattered throughout the different values here. And so we could apply our same classifier and say if y is greater than minus 0.2 or less than 0.6, we're going to call it blue and otherwise green. In that case, we actually only get one dot here that's called blue. And the reason why is because we have an entirely new set of data, and those data exhibit different properties than the data that we collected the first time around. And so our classifier that was actually perfect on the training set is quite bad actually on the test set. So it's important for us to keep in mind whenever we're building a prediction function that we want to be able to estimate what the error rate that we're going to get if we apply our function to a new set of data is. So the key idea here is then that the accuracy of the training set is going to be optimistic. As you could see from the previous example, we could perfectly create a classifier that classifies the samples into the two groups without actually being a classifier that will work well on a new data set. So in general, this is pretty much always true. You can always build a really, really accurate classifier in the training set by tuning to the observed data. So what we'd rather get is a better estimate of that data set from an independent set of data. So what we'd like to do is get the estimate that we would get from a test set. And we can't use the test set when building the model, or it will just become part of the training set, and we won't be able to validate the error measures on an independent set of data. So one way that we can do this is we can estimate the test set accuracy with the training set. And the way we're going to do that is basically by breaking the training set up in itself into a training and test set. So subsets of the training set that we're going to build and test our model on. So this is the basic approach of cross-validation. You take the training set, you split it into sub-training sets and test sets. Then on the sort of sub-training set within the training set, you build your predictive model, or maybe multiple predictive models. And then you evaluate your new predictive model on the test set that's the subset of the training set. Then you repeat and average the estimated errors. So this approach, this cross-validation approach, basically what it's trying to do is it's saying, okay, we're just going to take the training set, break it up into a sub-training and test set, and repeat the procedure just like we will on building our model on the actual training set and applying it to the actual test set. And then what we can do is we can estimate the test set accuracy. So this is used for picking which variables to include in a model, so this is sort of feature selection, or picking the type of prediction function to use. So if you have 3 or 4 different kinds of prediction functions that you might want to be considering, this will let you distinguish between them, or for picking the parameters in the prediction function. In general, the basic idea is you want to be able to compare a bunch of different predictors, and you want to be able to get an estimate of the error rate that they would have on an independent data set. So here are the ways that you can do cross-validation. One is you can do random subsampling. So for random subsampling, what you would do is you would just imagine each data point is just one stripe of this bar. So you can imagine you have this many data points across this bar, and then we're going to say, okay, we're going to assign randomly in this iteration this one to be a test set sample, this one to be a test set sample, this one to be a test set sample, and so forth. So we've taken our training set and split it into dark gray points, which are the training samples, and light gray points, which are the testing samples. Then we build the model on the dark gray samples and apply it to the light gray samples to predict and measure our error rate. Then we would do the exact same thing again, except we would reassign the training set samples to be a different random set of the samples in the training set, and our subset test samples would be a different random sample as well. Then we'd rebuild the prediction function on this training set and apply it to this test set and get an estimate, again, of the error rate that we'd have. We'd do this over and over and over again, and when we'd average the error rate to get the estimated out-of-sample error rate based on cross-validation. The advantage of random subsampling is that you can always balance the size of the testing and training sets. The disadvantage is that sometimes you'll get repeated elements when you do random sampling, and you'll sometimes you'll get elements that don't actually appear among the random samples. Another approach is k-fold cross-validation. So this idea basically is to take all of your samples. So again, we have samples here are represented by this bar. And we take the first third of the samples and call that the test set. And we take the second 2/3 and call that the training set. We build the model on the training set and apply it to the test set and calculate the error rate. Then we take the middle third and call it the testing set, and then apply the prediction model to the training set samples that are in dark gray, and then apply the prediction function to the test set and get the estimate of the error rate. Then we do the same thing for the last third. This would be 3-fold cross-validation. So we've taken 3 different subsets of the data and we've called them the testing data set. And it represents, by 3-fold, we mean we're going to take 1/3, 1/3, and 1/3 to be the different testing set sizes. If we were going to do 10-fold cross-validation, we'd break this whole set of samples up into 10 different chunks, and we would call each different chunk the testing set while we built the model on the other 9/10 of the data. An extreme example of this is leave one out cross-validation. So in this setting, what we do is we basically take one sample and we leave it out, and we build the prediction model on the rest of the data set. The training set is everything, all the samples but one. Then we apply it and calculate whether we made an error or not. Then we do the same thing, leaving the next sample out and the next sample out, so forth, until we've left each sample out one by one, calculated the prediction model on the remaining samples, and applied it to see what our error rate was. So the extremes here are k-fold cross-validation, where you have just 2 folds, or you just split the data in half, versus leave one out cross-validation, where you actually leave out each sample one by one. So leaving out each sample one by one is actually much less biased, because you're actually considering every possible sample as the test set holdout. The disadvantage is that since you're only measuring the error rate on one sample, you get sort of a variable estimate of the error rate. Meanwhile, if you split the data in half, say, you won't get an estimate of the error rate on every possible sample individually like you do with the leave one out cross-validation. So you might get a slightly biased error rate estimate, but it will be much more stable since you're actually estimating that error rate on many more samples. So it depends on what your application is, which of these sort of approaches to cross-validation that you might use. And we're going to be talking about how we use cross-validation for each of these different functions that we will be talking about for prediction in R. So here's an example of this. So suppose here then we've created this data set from the beginning where we had y and x values, and you now divide the y values up in half. So you take the first 5 y, x, and z values and you call that the sub-training set, and then you take the second set of y, x, and z values and you call that the sub-training set test set. And so then what we're going to do is we're going to calculate our predictive function on the basis of our first values. So in this case, it looks like if you're less than 1 and you're greater than minus 0.5, then we're going to call you a blue point. So then what we can do is we can apply that to the data set that was held out. So here we're going to calculate the estimated z values for data set 2, and we can plot them here. And so what we see here is actually that we actually get sort of not a very good error rate when we do that. We actually get one value that is the correct blue classification, whereas we actually have 2 other values here in this data set that should have been blue. So we can actually estimate what the error rate would be if we had a completely independent held out sample. So what this does is, instead of being overly optimistic like we were with the original training set, we can actually get a more accurate estimate of what the out of sample accuracy would be. So some notes and further resources. First of all, the training set and the test sets must come from the same population. So if you build training sets and test sets that don't reflect the way that the sampling of the population was done, for example, if you have a huge bias towards one particular group in your training set and not so much in your test set, you won't get very good estimates of the ultimate test set or validation accuracy. The sampling should be designed to mimic real patterns. So for example, if you're building a predictive model that on time series data, on data measured over time, and you want to be able to predict what's going to happen at the next time point, leaving out a random subset of data won't necessarily give you a good estimate of what will happen at the next time point, because you'll have scrambled up data values that should have been right next to each other in the sequence over time. So instead you might want to do something like sampling chunks of time in a time series. These cross-validation estimates have variance. So in general, even if you get a cross-validation estimate of the out-of-sample accuracy or the out-of-sample error, that estimate actually is subject to error as well. And so it's actually kind of difficult to estimate what that error is. So if you have 2 different prediction functions that have very, very similar cross-validation accuracies, it's very hard to tell which one of them will be actually more effective on an independent test sample. So this is a very nice discussion of cross-validation in R kind of generally. Then there's these tools in the CVTools and boot R packages for doing general cross-validation. We'll be talking a little bit more about them in later examples in the class, but we'll also be talking about the cross-validation functions that are built into specific prediction functions.